So starting off in section 1.7, we're going to talk about uh, 1.7 and combining functions. And we're talking, basically what we're talking about today is doing arithmetic with functions. So can we think of some examples of how we might combine functions using arithmetic? What kind of thing could we do to two functions to combine them? Add them. So we can add. And let me write down an example, just easy example. So say we had 3x squared plus 2x plus 1 plus x squared plus x. So those are our two functions. Here's one function and here's the other function. What's kind of the Algebra 1 way we talked about combining functions this way? Combine like terms. That's exactly what we're doing here. We're just combining like terms. And addition, what's the next easiest one we could do with functions? Subtraction. And for these, combine like terms. That's all we're doing, combining like terms when we add and subtract functions. And to subtract, we just have a minus sign here, and then we subtract instead of adding, like terms. Now we're going to move up, make it a little more difficult. What's the next most difficult arithmetic operation we could do? Multiply. So we can multiply functions. And that would be something like 3x squared plus 1 times x plus 3. Something like that. And for this, and what's the property that we're using when we multiply these together? FOIL is our description, but what property are we using? Distributed. We're distributing. So when we multiply, we're thinking we're distributing. The FOIL is a way to help us remember how to distribute. And then the next most complicated, division. So those are our operations. I'm not going to go through a lot of examples with these. We know how to do these things. We're just doing these operations. I want to write down a little bit of notation though. So we're going to say that f of x and g of x are functions. And we'll get into, on Friday, we'll get into a little more detail, remembering what we mean when we say a function, because we're going to be talking about inverses. So we'll get into a little more detail about function. F and g are functions. Our notation for addition, we say f plus g, and sometimes you'll see f plus g of x. This doesn't mean we're multiplying, this means f of x plus g of x. So this is our notation for adding two functions, f plus g of x. Same thing for subtracting, f minus g. Sometimes the x won't be there, it'll just say f plus g, and they're just saying add those two. F minus g of x is just f minus g. And when we multiply, our notation for multiplication, we say f times g of x, and that's saying multiply those two together. and then our division f over g of x, and this is saying divide f by g. And what do we have to be careful with here? Well, we have to be, so this, make sure we do it in the right order. And because we have a fraction, g of x cannot be 0. That's very good. So when we're doing a quotient, when we're doing division, we want to make sure the denominator is not 0. So sometimes the problems will say find f of x divided by g of x and its domain. When they ask you to find its domain, they're saying, is there anything that we have to restrict from the domain? Does this quotient give us a problem? So that's what we have to worry about g of x being 0. Everybody okay with this? Hopefully nothing new, nothing earth-shattering here. All right, so these are easy ways of combining functions with arithmetic. Can anybody think of what's the next most complicated thing that we could do to combine functions? So these are all our arithmetic operations. That's another way we can put two functions together. Let's see if we can. I'll give you a hint. So we call this property the distributive property. Is there another property that we can think of? Give you a hint. It starts with an S. And we do it a lot with numbers and functions. Substitution, very nice. We can substitute a function into a function. So we substitute numbers into functions. We can substitute a function into a function. Do we remember what that's called? What we call it when we substitute a function into a function? F of g of x, right? We'll talk about that in just a second. Do you remember what f of g of x is called? Starts with a C. It's a composition. So compositions of functions means we're substituting a function into a function. Not function. And the way we write a composition is we say that f of g of x. And what we're doing, what this is telling us to do, is substitute g into f. So I take g and I put it inside the function f. We think of g, the way we describe this is when we write it this way, g of x, we have f of g. G of x is the inside function. That's the one we're putting into the other. And f is the outside function. And we'll use those terms in a little bit. So a way to help us think of it. So g is the one we're putting inside. And if we can write it in the other order. We could say g of f of x, and that's going to be g, and we're substituting f inside g. So now the inside function would be f, and the outside function would be g. So that's how we form a composition. Substitute a function into a function. And the domain of a composition is a little trickier than the domain of other combination of functions. So what I'm going to say, it sounds complicated. It's not as complicated as it sounds. So the domain of a composition, and before we write this out, let's remember domain. When we're talking about domain, what are we talking about?
Wherever x is between
So
between 5 and
okay, so we're talking about the what x is between. So we're thinking of the x values. What are the x values? The domain is the x values. What are we allowed to put in the function? So the x values. So I was just focus it a little back. Oh yeah, and it was fine. You was between something and something. Often it's between something and something. Nice functions is between negative infinity and positive infinity. Sometimes they're not as nice, and we have to do some other things, figure out some other things. So the domain of a composition is all x values and I'm going to say so that g of x, our inside function, is in the domain of f. And what this means, what this boils down to, is that when we're forming a composition, we're putting x into our function g first. So first off, we have to be careful of the domain restrictions for g. We have to pay attention to the domain of g. And then whatever we get out of that, whatever comes out of g of x, whatever our result is, has to be in the domain of f, because we're plugging g into f. So what this is telling us is when we're looking at the domain of a composition, we have to look at the domain of the inside function and the domain of the outside function. We have to look at two pieces. And we'll do some examples in just a minute where we have to be careful with that. So when we're thinking of a domain, we have to think of two pieces. That's what this is telling us. All right, let's do a couple of examples. Are we good so far? What a composition is. Substitute a function into it. Composition is extremely important as we move forward. Lots of functions. The nice thing about combining functions is we can make more complicated functions out of simpler functions. If we can think of them as the functions in terms of the simpler pieces, it makes them easier to work with. Rather than looking at a big complicated thing, we're looking at pieces, simpler pieces that are put together. We can focus our attention on the pieces rather than on the complicated big thing. All right, examples. Let's form some compositions. So let's say that f of x equals x squared plus 2x. We'll do a couple easy examples here. X squared plus 2x, and g of x equals 2x plus 1. We want to find f of g and g of f. So just as a reminder, f of g of x is f of g of x. So this is telling us everywhere we see an x in f, we're going to plug in the function g. So how are we going to form our composition? F tells me to take x and square it and then multiply x by 2. So what am I going to square for the first term here in f of g? 2x plus 1. Very nice. So there's 2x plus 1 squared. I'm taking g, sticking it in there for x, plus 2 times, not x, but 2x plus 1. And then we simplify this. This one we can simplify, not all of them we can simplify. So this is, just as a reminder, 2x plus 1. This is not 4x squared plus 2. We have to do this. And then here we distribute, so 4x, this one is 4x plus 2. So when we multiply this out, we get what? 4x squared plus a 2x and a 2x plus 4x plus 1. So that's what this is. Plus 4x plus 2. Combine our like terms. Now we're just adding two functions. And we get 4x squared plus 8x plus 3. And that's our composition. And let's go the other way, g of f of x, and that's g of f of x. So we're plugging in f into g. So how are we going to form that composition? Here's g. This one's easier. 2 times x squared plus 2x, nice. And then it just tells us to add 1 to that, plus 1. And this is 2x squared plus 4x plus 1. In general, f of g does not equal g of f. It's only in certain cases when that happens. And we'll talk about that on Friday, because when we form the composition f of g and g of f with a special kind of function, they turn out to be the same. And that's when we do that, we'll be talking about inverse functions. So inverse functions when we talk about inverse functions, we'll be talking about compositions. Let's think about the domains of these two compositions. What would be the domain of this 4x squared plus 8x plus 3? Any real number. All real numbers. What's another way we can say all real numbers? Negative infinity to positive infinity. We could write our domain with interval notation. Like so. That means all real numbers. Why do I use the curved parentheses rather than the square brackets? It can't equal infinity. There's no number infinity, because we can always find a bigger number. And this same domain here. So we don't have to worry, we don't have any restrictions here. These are nice polynomials, so we don't have restrictions. Now let's look at a couple of compositions, and we'll talk about their domains, where we have to be careful about the domain. All right, are we good on these examples? Any questions? Okay, pretty easy forming composition. And just be aware, sometimes when you form compositions, here we could simplify, we could multiply some things out. Sometimes all you can do is just write the one function times the other function. It doesn't get any simpler than that. So, just be aware of that. All right, let's say f of x, I'm going to do two examples of this to show you how we have to be careful. F of x equals 1 over x minus 2, and g of x equals the square root of x. We want to find, problem asks us to find f of g of x and its domain. All right, so let's find this composition, f of g. So I'll get us started. F of g of x equals 1 over. And what do we write in the denominator? Square root of x. We're sticking in square root of x every time we see an x. So we get square root of x minus 2. And what's our domain? We have a fraction here, so what do we have to restrict from our domain? We can't have the denominator equal to 0. What makes a denominator 0? X is not equal 4. So this one was pretty easy. We can look at the composition and figure out x cannot equal 4. So that keeps the domain, that makes sure that g of x is in the domain of f. That's what the thing we said before. If we restrict 4 out of the domain, that makes sure that g of x, everything we get when we plug in x for g, everything we get here is in the domain of f. So this would be our restriction. So how would we, if this is how we're restricting, how would we be more precise in saying our domain? Well, what if x does not equal 4? What is in the domain then? All real numbers except x equals 4. So we could say real numbers x does not equal 4, or all real numbers except x equals 4. Some kind of so our domain is what is allowed. What is allowed. So to be more precise, we'd say all real numbers except x equals 4, something like that. If we wrote this, let's make it a little more interesting. How would we write this in interval notation? Negative infinity, comma 4, curved bracket here, can square or curved bracket here. Can x equal 4? No. Curved, so not equal. And then 4, comma, infinity. And the way we put those together is put a u. U. So that would be another way we could write it. Any of these is fine with me. If you said x is not equal 4, I'm not gonna dock you for that. Just to be more precise, we'd say all real numbers except x equals 4, or write it in this interval notation. All right, let's look at one where we have to be more careful. Let's say f of x equals 1 over 1 over x squared plus 2, and g of x equals the square root of x. And we're doing the same thing. We want to find f of g and its domain. So f of g of x. So let's form our composition. 1 over, plugging in g for x here, square root of x squared. What does that give me? X plus 2. So if I just looked at this composition, what would I say is restricted from the domain? We're going to say x not equal negative 2. Remember, we're starting off by putting x into g. What's restricted from the domain of g? Negative numbers. We can't plug in any negative number into g. We have to look at the restriction on the inside function as well, because we're plugging our number into g first, and then plugging that result into f. So our restriction for g is negative numbers. How do we write that? Do we write x not equal negative? You could write that. If you wrote it out verbally, you could say x cannot be a negative number. Greater than, or yes, you were right, greater than, because square root of 0 is 0. So 0 is okay. So we'd say x greater than or equal to 0. So that takes care of that -2, but it makes sure that when we plug a number into g, it's not negative. We have to make sure we look at the restriction on the inside function. Yes?
So the example that we did before this, g of x is also square root of x.
Mm-hmm.
But why can that one be always this
Did we make a mistake? I think we did. Because when I plug in for g here, can I plug in a negative number here? No. So we forgot to restrict the negative numbers here. So we have we're going to say x does not equal 4. And we're going to take away this interval, right? So x can't equal 4, we know that. But what else can x not equal? Negative numbers. So x greater than or equal to 0, and x cannot equal 4. Good catch. And just so you know, occasionally I'll make arithmetic errors, things like this, and we do that just to make sure you're paying attention. That's the theory I'm going with. All right. So we do have to, g of x was square root of x, so we do have to restrict the negative numbers from there. So we have x is greater than or equal to 0, and x is not equal to 4. Here we just have to restrict the negative numbers. All right, we good? So we have to make sure we restrict the domain of the inside function. All right, so all I want to do is next is just talk a little bit. You'll see a couple of graphical problems in your homework, and I want to make sure that we can pick out combinations of functions graphically. So you'll see a couple of examples like these in your homework. This is all I wanted, the details I want to talk about. Just want to talk about a couple of things you'll see in your homework. So let's say we have two graphs. And I'm just making this up. This is F. And this graph gives me G. So there's G. And this says, this is 13, and this is the point 13, 17. That's that point. And on G, that's the point 3. And this is the point 3, 13. And we have these two graphs, and the problem asks us to find f of G of 3. And this is telling us we want to find f of G of 3. Just another way of writing the composition. So how are we going to do this looking at our graphs? Well, let's look at the inside function first. What's a G of 3? Go over 3, go up here to this point. So what do we get? 13. What's f of 13? 17. So this is telling us find G of 3. G of 3 is 13. And then we're evaluating f at whatever we get there. So G of 3 is 13. F of 13 is 17. So f of G of 3 equals 17. So we can pick out these compositions from our graphs. Are we good there? All right, let's look at one other example with a graph. Problems like this show up on your homework, and I'm just making up something like this. And these are supposed to line up. So this is, let's say this is 2, 3, and this point is 2, 10. That's 5, 5, and this point is 5, 6, etc., etc. And this is f here on top, f of x, and this is g of x on the bottom. And the problem says find f plus g of 5. How would we find f plus g of 5? Well, this is saying f of 5 plus g of 5. What's f of 5? 6. G of 5? 5, and that equals 11. So we just add the two values. I had students in the past use the try to construct try to draw a new graph using these and kind of finding the slopes and adding things together, finding the equation of the lines between here, and then adding the equation of the lines to come up with a graph of f plus g. Find f plus g of 5. All we need to do is add f and g at those points to find f plus g. So don't make those problems more complicated than they need to be. All right, everybody good? Yes.
So whenever you're talking about like of 5, is it always the x-axis value?
Yes. So that when we're saying f of 5, this is our x value.
And it's always going to be the x value?
Yes, for the most part. Sometimes we'll talk about a function of y, but we'll make sure we're saying this is a function of y, and then we're plugging y values. But generally when we're talking about functions, the values that we're putting in are x values. Okay? Mm-hmm. All right, homework. My student in the last class told me how I could consolidate this. When Mr. Leader and I picked the problems last year, we had trouble writing the numbers in a nice, always writing the numbers in a nice shorthand way. So this is 7 through 55 every third. And it's also on the board over here. I just wrote them all out over there. 59, 60s. And these problems, for the most part, they're not long, they're not involved problems, so they don't take a lot of work. They don't make them more difficult than they need to be. And some of the problems say they'll ask you to do this and do that, and then verify the results using a graphing utility. If it says at the end of the problem, verify the results using graphing utility, you don't have to do that last bit. There are some of the problems in the homework that just ask you to do something in your graphing calculator, and that just means to do the graph or do whatever it asks you to do in the graphing calculator. But if it asks you to do a bunch of stuff and then verify using your graphing utility, you don't have to do that last step. All right.